Okay, hello everyone. Welcome to the Seminario del Instituto Avanzado de Cosmología. We're gonna have this time Dr. Tanja Rindler-Daller, who is very kind to participate in our seminar. I'm just gonna give a little review of her career. Tanja obtained her PhD degree at the University of Vienna in February 2007, and she graduated with a thesis entitled Contributions to the Theory of Vortices in Rotating Bose-Einstein Condensates, under the supervision of Jacob Vanson. She then moved to Germany to do a two-year postdoc in the University of Cologne, and she has held two more postdoctoral positions, one at the University of Texas for 3 years, and one at the University of Michigan for 2 years until 2015. She then moved back to Vienna, where she has been a lecturer from 2016, and she has also been awarded 2 important fellowships, the Lise Meitner Fellow and the Elise Richter Prize Fellow, both at the Institute of Astrophysics at the University of Vienna. Tanja's principal interests are cosmological structure formation, galactic dynamics, dark matter, and effects on stellar evolution of dark matter, as well as Bose-Einstein condensations, quantum phase transitions, and applications in astronomy and cosmology. She's also 20 published papers, and in this occasion, she will talk to us about the cusp-core problem in galaxies and a possible solution through the scalar field dark matter with repulsive self-interaction. So without further ado, I'll give you Tanja for her presentation. Thank you, Tanja, for participating with us.
Yeah, thank you. Muchas gracias por la invitación. Yeah, it's a great pleasure to give a talk in this seminar, in this institute. I hope that maybe one day I'll see many of you in person again. Yeah, so I will talk about some results of scalar field dark matter, especially with regard to the cusp-core problem. So this is by no means a review talk, but I will only sort of pick a few things to make a few cases, and I apologize if I do not give a proper review, including all the references and people. Most of the things I show has to do with work I have been involved, and so I'm thanking my collaborators, which are on the papers that I will present, who are Paul Shapiro and Taha Woodboy at UT Austin, and then my students in Vienna, Kevin Pils and Horst Feudel. Yeah, scalar field dark matter is a candidate which has been championed early by Mexican groups, especially and foremostly. And I'm just giving a few names which come up from my mind, but just as a flavor, there are many other people involved. So it's actually been championed by a lot of Mexican groups, and more than 20 years ago already, and there are some papers from the 90s even. And ever since, it has gained more and more interest also by other people and other groups. And some people or groups may have not been aware so much about previous work, or they may be aware and do not appreciate it. But in any case, often people come up with new names or different names, and then you think it's a different animal when in fact it's the same animal. However, it is true that scalar field dark matter does include a lot of, in principle, a lot of different particle models. It turns out that ultralight axions could be modeled this way, or bosons in general, if they undergo Bose-Einstein phase transition in the early universe, say. And so there are different names often and different particle models, but the underlying framework might be very general. So just to say that there are a lot of words around for things which are often modeled in the same way. So, as I said already, ultralight axions are somewhat similar to the QCD axion, but often people neglect self-interaction. So it's more like a free field anyway, or people call it quantum wave dark matter or fuzzy dark matter. And the idea is that in the end you have only a scalar field, which is a proxy for the many-body quantum state of some system, which actually consists of many, many particles, bosons or pseudoscalar. And so, and then of course you write down a Lagrangian, and you may have more or less terms that describe either self-interaction or not. And so you can of course amend the model and say, okay, these particles might interact also, so you can include self-interactions also in this model. They might be attractive or they might be repulsive. And I'm actually in this talk focusing on the case where you have a repulsive self-interaction between the particles included, even in a regime where that repulsive self-interaction is strong, which is also called Thomas-Fermi regime. So this is my main focus in my talk. But in any case, all this, as I said, you can come up with a field description, and the equation of motion is often used for all these kind of models. And I will show you in a second how it looks like. And also, scalar field dark matter has the nice property that in principle you can model very ultralight particles. And if you have ultralight particles, the characteristic length scale that you get for structure formation is different than in CDM. And so CDM, astronomically speaking, has had issues, so to speak, on small scales, on dwarf galactic scales. And they go under names like the cusp-core problem, missing satellites problem, too big to fail problem. And the cusp-core problem says, for example, that CDM actually predicts cusp, so the densities in the centers of especially dwarf galaxies are very high, while observations may tend to give you sort of more flat cores. Similar issue is the missing satellites problem, where for a long time people have said CDM predicts a lot of substructure. No? You should expect much, much more dwarf galaxies in the local group, in the local void in general, as we see. And of course, there are different ways to resolve this. Either you say, oh, there's an issue with CDM, and maybe the dark matter has different properties on small scales, different from CDM, and so it's actually a problem which you solve on the dark matter side. Or you say, well, it's not a CDM problem, it's more a problem about baryonic feedback, because of course galaxies are more complicated than just the dark matter. So you have gas in it, you have star formation, you have a lot of feedback going on, and maybe there's a way to solve all these small scale problems with baryonic feedback. And I think it's still fair to say that it's not quite settled, this question, because also the baryonic feedback things often invoke some recipes, right? It's not often clear how much feedback is really allowed with observations, and so it's still an open question. But of course, for theorists or cosmologists, any way to think of alternatives to CDM is interesting. And so the astrophysical motivation to consider alternatives are the small scale problems. But of course, another motivation is the mere fact that we have not detected yet any CDM candidates so far either. So there is motivation to consider alternatives. So, and here for the scalar field dark matter, this characteristic length scale below which structure formation should be suppressed, or below the scale where densities should be sort of reduced, of course depends on the particle parameters. And if you only have a free scalar field, free I mean with no self-interaction, the mass is the only typical parameter you have. And the mass range I give you down here is sort of the typical range people consider if they also want to resolve the small scale problems. Because if the mass becomes too high, the model becomes very CDM-like again. And so there's not much of a difference you see between CDM and scalar field. Things change if you include a self-interaction, because then you have an additional parameter, right? And of course, then you have another parameter to play with. So this is not just to show you people have checked all these things in terms of the linear structure formation side, for example. So if you calculate linear structure growth and compare with CMB spectra or power spectra, you can see what differences you get compared to CDM. And so it has been known for a while that here for the power spectrum, say on the left panel or the right panel down here, the black curve sort of is CDM. It has the shape we all know. And if you have scalar field dark matter, fuzzy dark matter of a certain mass, which is small enough that there are deviations to CDM, of course you have a cutoff in the power spectrum. So structure suppressed compared to CDM. This is what you want, no? I mean, this is kind of the mass parameters you want to pick if you want to say, oh, I'm suppressing structure, so in order to resolve possibly the small scale problems. Good, yeah, and of course these length scales which determine the cutoff, they are related to the Jeans length of these models. And the Jeans length, of course, also related to the nonlinear scales, like the virial scales, virial radius. So again, just to emphasize again the parameters. If you have models without self-interaction, I call them fuzzy dark matter, okay? Only the mass matters. And in that case, the length scale, which is characteristic, especially for nonlinear scales, halo scales, is the Broglie wavelength. And it goes like 1 over the mass. And the Broglie wavelength, of course, has a velocity in it, so it's environment dependent. But if you consider a halo, you would typically pick a velocity that is characteristic for the halo, which could be the virial velocity. Now, if you add self-interaction, then you have an additional parameter, as already said. I'll call it G here. And of course, now you can even go further and say, okay, there might be a regime where the self-interaction is sort of dominant, and that's called the Thomas-Fermi regime. And it turns out in that case, there is a length scale, a related length scale, which is, if you think of a halo structure, which is close to, or actually you can calculate it, the length scale of an n equal 1 polytrope. And I call it RTF. This is the Thomas-Fermi radius. And this will be important in my talk. And this scale depends on the ratio of G over M squared. So it's not only M which comes in, but it's the combination G over M squared. So in other words, suppose I pick a Thomas-Fermi radius of around 1 kiloparsec because I say I want to have a length scale such that maybe I want to have a core in dwarf galaxies of roughly the size 1 kiloparsec. Suppose I pick this. Then I get a value for the ratio G over M squared. It says it's a number in these units, which is maybe somewhat funny, but never mind. But my point is, if you pick the 1 kiloparsec, say, the mass M here in the denominator, in principle could be higher, much higher than the whatever 10 to the minus 20 eV I showed you before, if you just adjust the G as well, right? So the Thomas-Fermi regime allows you in principle to consider models with much higher M than the ones you typically are thinking about in fuzzy dark matter, if your G is just also accordingly set such that the RTF is a kiloparsec again. So, but that means in principle, if your mass can be much higher, then we just saw that the Broglie wavelength will be much smaller. And in fact, in this regime, it can be shown that the characteristic halo core that you get in such halos is roughly of this size RTF. And this RTF is typically much larger than the de Broglie length of your particle. This is different to fuzzy dark matter, I mean the models without self-interaction, where it has been shown, now I should say more, that their halo core size is of the order of the de Broglie wavelength, roughly factors of a few, say. And yeah, so that means in this case, the halo core size is really given by the de Broglie wavelength. And obviously, if you say you want to have 1 kiloparsec core, well, that means your de Broglie wavelength has to be roughly kiloparsec. That tells you the mass, m should be correspondingly small. What's important also in the fuzzy case, right, in the fuzzy dark matter case, the size of the core goes inverse to the mass of the core. While in the Thomas-Fermi regime, the core size does not depend on mass. And this will be important for the next thing. Yeah, I'm stating quickly the equations of motion, which you probably all know well, because many of you are acquainted with scalar fluid dark matter. So briefly only for halo physics, it's for the physics of halos, it is sufficient to consider the Newtonian regime, don't need GR and all that. And then you couple a Gross-Pitayevsky equation, which is nothing but a nonlinear Schrödinger equation, wave equation. You couple it to the Poisson equation. And that's your equations of motion. Here I include a scale factor in principle, because you could still study the system in an expanding background, but you can also consider static background. Also, you can reformulate these equations, which have also been done in the literature quite a bit, into in a hydro version. So by making this kind of polar decompositions or Madelung transformations of the Scalar field psi, you can come up with a definition for velocity, which is related to the gradient of the phase of the field. And then you can come up with hydrodynamic equations. Continuity equation stated here, and then a momentum conservation equation, or an Euler equation, if you will, stated down here. But the upshot now is that in this Euler equation, so to speak, you have pressure terms, which are different to just a dust-like fluid. You have a pressure which comes from so-called quantum pressure, which is related to the fact that you're actually considering here this quantum system. And if you have self-interaction, you can also think of a self-interaction potential, which is your VSI, and this gives rise to a self-interaction pressure. So the gradient of this potential gives you pressure. And so you have a quantum pressure and a self-interaction pressure in this Euler equation, so to speak. So in principle, now you could go now ahead, pick either of these formalism, pick your initial conditions or boundary conditions, and study whatever you want. Either a single halo or a simulation of many halos in a static background or in an expanding background. In principle, this can be done, but it is very hard. Yeah, so actually 3D fully fledged cosmological simulations in representative volumes are actually impossible, and probably will be impossible for some time. So most of the literature has actually resorted to 1D models for good reasons, because it's a bit easier, but not easy. But yeah, so these are the equations of motion that you would solve. Okay, as I said, I'm not gonna go into a review. I'll sort of jump ahead to some current results in a say, and then leave out a lot of other literature, but I want to make a point sort of quickly, and so I have to get there quickly. As I said, you can do this in 1D, and 3D is very hard, and so there are few people who have tried to do this in a 3D simulation, where you have, for example, fuzzy dark matter, no self-interaction, and you want to simulate halo formation. So what happens often, people just take small boxes like 1 megaparsec co-moving on a side in an expanding background, say, and have some, or a static background even, and have maybe some small things, sort of like cores, sort of primordial cores, sort of come together, merge, and so on, and try to create halos. And what you see here is a picture from this paper, Marzo et al. 2017, where they sort of did this, and this is a picture of a halo, so to speak, that you get. And you see it's a very wobbly thing. It's got a lot of this quantum interference, wave interference, and yeah, it looks very different in a sense than for CDM. And in the center, you can see this kind of core. And what's interesting for us, if you spherically average and try to make some density plots, right? You have the halo density profiles here. So the density is a function of radius. And what you see is, and what people also in other simulations have seen, is that you end up with some core envelope structure. You have a central core of that halo and you have an envelope of the halo. And the envelope, people claim, is CDM-like and FW-like, meaning that the fall-off is sort of similar to NFW. Also, well, I couldn't tell you in principle whether these points down here go like R2 minus 3 or whether they rather go like R2 minus 2, like an isothermal sphere, say. But anyway, the envelope is similar to profiles which you might use for CDM models. However, in the centers, you don't have a cusp, but you have a core. The core may have certain properties. And that's what people find. In principle, they find that in the centers, you find cores which are similar to the solid tonic cores, which people have found already previously in 1D simulations and maybe in some analytic, semi-analytic studies. And so the point here is that core is roughly of the order of the de Broglie length of the particle. And what's also important, as it's relating to what I just said, the central density of these core regions, since the radius goes like 1 over m, I told you the radius goes like 1 over m, the density goes like m to the 4. So central density goes like core mass to the 4, meaning it increases quite a bit if you increase the core mass. Also, what simulations have found, there are global scaling relationships between core and halo envelope. So if in principle if your halo mass rise, the core mass also rise. So for larger halos, you expect more massive cores. That means their density is also proportionally higher. So, okay, this fuzzy dark matter again has been pointed out now for some time that it's probably not able to resolve all small scale problems. Why? So there is a work by Victor Robles, actually, whom some of you may know, and Bullock, Boyle, and Kolsch in 2019, and they looked at this fuzzy dark matter model in more detail. They call it here SFDM. Okay, so there's some confusion now in the notation, but what they really consider is a model without self-interaction. So you only have the mass as a free parameter. And they now say, okay, what if you want to solve the too big to fail issue and the other issues, cusp-core? So if you want to make sure that the densities or velocities of halos of a certain size are in accordance with data, you have to pick parameters, right? So what I'm showing here, a plot of their paper. So it shows velocities, asymptotic circular velocities versus radius, both panels, for halos of 10 to the 10 solar masses. Basically, this one has 10 to 9.5, but roughly 10 to the 10 solar masses. Of course, his data points included from local group dwarfs or satellite galaxies, and of course they have error bars. But the upshot is here, the only thing you should notice is that the CDM curves are the dash curves. They do not go through the data, but the fuzzy dark matter curves, sort of the purple and the whatever turquoise, they do better represent the data. So for these models that they pick, this is now the mass in units of 10 to the minus 22 eV. One case is 0.8 and the other case is 2.5. They say, okay, well, no, both models are somewhat okay. Maybe this one with 2.5, no, sorry, the one with 0.08 fits the data better. But in any case, it fits the data certainly better than CDM. Now you've picked your parameters for the dark matter, no? For this fuzzy dark matter. But could you also explain the rotation curves of higher mass halos? And they say, no, you can't. If you pick the parameter such that the too big to fail issue is resolved, so to speak, you fail for higher mass halos. So the cusp-core issue is an issue for higher mass halos, roughly 10 to 11 solar masses. So if you look at those halos and those rotation curves, there's again data included here. Again, what you should look at is that for CDM, now the offset is not as bad because CDM does better for these halos than for the smaller ones. However, the other two cases, the fuzzy dark matter cases with this choice of mass, they are not representing the data well. And the authors make a point why they're even failing, they're worse in a sense in representing the data than CDM. So they say, well, it appears that fuzzy dark matter cannot resolve, at least not all of the small scale problems, because if you make sure that the parameters that you choose to resolve the too big to fail problem will not at the same time resolve the cusp-core problem. Okay, this is fuzzy dark matter. Now, what about the Thomas-Fermi regime, the other limit? This is harder. Harder, how should I say? This is even worse in a sense because I've shown you that there is a length scale which is this Thomas-Fermi radius, and it is much larger than the de Broglie wavelength. So in principle, you have more length scales, but you cannot resolve them all. So the issue with resolution, which you already have, is fuzzy dark matter, is much worse for the Thomas-Fermi regime because now your de Broglie wavelength is way smaller than in the fuzzy dark matter case, and you can't possibly resolve it. I mean, not for the purpose at hand. So there are no simulations. Now, had been no simulations. So we try to circumvent it in a sense by saying, okay, what about trying to devise a mechanism to come up with some formalism that doesn't care about the de Broglie length? Or another way to say it, let's suppose that we do not need to resolve length scales on the order of the Broglie length, because they're small, but we need to resolve length scales of the order of the Thomas-Fermi radius. And so we were thinking of a way to do this, and we actually devised a fluid approximation for scalar free dark matter in the Thomas-Fermi regime, which I can't not go into any detail. If you're interested, you can look up the paper. But in essence, it means that we sort of coarse grain over the scales of the Broglie wavelength, but make sure that we have a formalism that is valid on large scales and can resolve scales of Thomas-Fermi radius. And what we find and then we do a 1D, we use a 1D Lagrangian hydrocode to calculate spherical infall, meaning to calculate gravitational collapse of a single sort of a Jeans unstable perturbation in order to see how it would form a halo and what the halo would look like, what structure it would have. And what we find is that halos that are formed this way also have a core envelope structure, similar like fuzzy dark matter. So you have a core and you have an envelope. The envelope is somewhere is CDM-like, so to speak. And the core is really very close to the n=1 polytropic core that you would sort of come up with a hydrostatic calculation if you only had sort of the self-interaction pressure. So in spirit, it is similar than what people find for fuzzy dark matter, but just now exemplifying the physics of the self-interaction pressure, which is more potent here, because you have no self-interaction in the other case. But the upshot is that actually all this, the physics under the Broglie scale, which is due to the quantum pressure, is now modeled in an effective way. So sort of like, yeah, as I said, a coarse graining in an effective way, all this wobbling in the sense which you've seen with the fuzzy, instead of coarse grained over, and it can be shown that this, in an effective way, this quantum pressure can be modeled like a velocity dispersion. And this velocity dispersion pressure, so to speak, holds the envelope up against gravitational collapse. So it's similar maybe in a sense like then in the when you think of for example the stellar velocity dispersion elliptical galaxies, right? You have a lot of stars on orbits, and in an effective way they give you a velocity dispersion, and somewhat similar happens here in this coarse-grained model. In any case, it can explain, in a sense, explains why the envelopes look similar to CDM, because the way the formalism works, you can show that the fluid approximation in the envelope is similar to the fluid approximation for CDM also. So. And this is just an example, right? So what you see is a density profile, density versus radius for such a halo in the Thomas-Fermi regime. It has a core here and then an envelope out here. And there were several steps to our analysis. In the first round, we had to sort of do this in a static background. So no expanding background here. I will get to this shortly. And yeah, so this was just the kind of confirmation what maybe some people have already anticipating that here too, you might expect a core in an envelope. So the CDM case is red, right? This is fluid approximation for CDM, is already around for some decades. So this is sort of the starting point for us to devise our model. You can see, of course, CDM would have a cusp, right? Its density would just grow indefinitely in here, while SFDM-TF is the black curve. It gives you the core in the center instead. And yeah, and these are just different timestamps, snapshots, so to speak, which are but this curve here is the halo profile in our case. Okay, we calculated these things. We also came up with some approximate models, either a fitting function. Once we had found our 1D halo profiles, we could devise a fitting function, or we could also write down a kind of semi-analytical model, which considers which stitches together a core with an envelope. And so we compared this to our numerical simulations, but I have no time to go into this, I'm afraid. But here is now our version of sort of the Robles et al. Figures of before, but now we include this Thomas-Fermi regime. So this is again a plot which shows smaller halos, 10 to the 10 solar mass halos. There's data again here plotted for 12 galaxies of this sort of roughly size. And what you can see is that the dash curve CDM does not represent the data, while the gray line here is a fuzzy dark matter model with the 0.8 times 10 to the minus 22 eV. It goes through the data, so it seems to be fine. And the other curves you see, mostly the black one I want to draw your attention to, is our model, the Thomas-Fermi scalar field dark matter, and that too goes, well, sort of is a better representation of the data. Yeah, and now for larger halos, we found that actually the Thomas-Fermi case can also do better. So in the next slide, I show you again velocity plot for the larger halos, 10 to the 11 roughly. And here too, the dash curve is CDM. There's again data, of course, with large error bars, but never mind. The gray curve is the FDM model, and the other curve is sort of the scalar, the Thomas-Fermi scalar Friedrich model. And here's the upshot. No? I mean, Robles et al. They have said, well, FDM cannot resolve both, no? Too big to fail and cusp-core. And we say here, oh, if you pick a Thomas-Fermi radius which is big enough, that's important. I didn't mention that. It has to be kiloparsec size. Here we pick 4 kiloparsec. Then you can represent the data well for both cases, right? I mean, both halo mass ranges. In contrast to CDM and in contrast to fuzzy dark matter. That was good news, no? I mean, I would think that that is a good news because it says, oh, great, can solve that. And lately, with my student, we also looked into the issue, what if you include baryons, right? I mean, all these calculations we did was dark matter only. Also, this Moch et al. Simulation I've shown you before, fuzzy dark matter was also dark matter only. What if you include baryons? It's very hard. And so a very poor man's first approach is to say, okay, let's just do adiabatic contraction. Let's just pick some halo model and do adiabatic contraction. That's what we did with my students. So we picked some semi-analytic Thomas-Fermi scalar free dark matter halo model, the ones actually from our previous work, which were analytic approximation. And let's add baryons to it. Let's do adiabatic contraction. And what will happen? And here too, what we find is, if I first show you the right-hand side, this is CDM. So you can see the green things here. This is data again, of course, with error bars. And what you can see, the dash curve is sort of a CDM only curve. But now we include baryons, and the fraction of baryons is roughly 0.1, say. No? I mean, in between a range which includes 0.1, and do adiabatic contraction. Of course, that will crank up the density in the center where the baryons dominate. It will also crank up the velocities in the centers. No? That's what we see. No? The curves which you see here, these colored curves here, are sort of the post-adiabatic contracted halo centers with different baryon fraction. And you can see, of course, for CDM, it cranks up the density a lot, and you're way off the data. If you do the same with scalar free dark matter and Thomas-Fermi for a core radius which is large, I mean 4 kiloparsecs, say, same choice than before, you do the same thing, and what you see is that the curves you get, which are the colored curves down here, they do still go well through the data. Forget about these curves up here. I will come to them shortly. But look at these curves first. So the colored curves here, they do still go nicely through the data. So it appears that scalar free dark matter Thomas-Fermi, if you have big cores, like, I mean, above 1 kiloparsecs, say a few, even the addition of baryons may be fine for this poor man kind of calculation, because we do not include baryon feedback, right, and all this. So this is just the very first consideration. So that's fine. That is all good news. In that sense, the cusp-core problem can be resolved, and too big to fail and whatnot. But the thing is, yeah. So in the course of our work on the halo formation, we needed to come up to also calculate realistic halos in an expanding background. That's what we did too. So you see the same kind of profile like you saw before, but now in an expanding background, in a more realistic initial conditions. And also you find a core, and you also have an envelope which one can show is close to CDM. This is a very small core here of 10 parsec, by the way, but since we have a 1D Lagrangian code, we can resolve these small cores. This is the advantage of 1D over the 3D, which is almost impossible. But why would we choose such a small core? And well, the point is that during this study, we came upon an issue because we realized that structure formation is subtle. So the point is, and I have to speed up, sorry.
No worries, we have time.
Yeah, I'm sorry, I'm being slow. And I mean, every dark matter model has a gene scale. But for CDM, the gene scale is so small that you hardly ever care. I mean, you don't care in terms of structure formation or galaxy formation. For the other models, you care. Warm dark matter. If you know, I've showed you the cutoff in the power spectrum. We know gene scales are relevant in this model. Same for fuzzy dark matter and same for scalar dark matter in general, Thomas-Fermi. Now, it turns out that the gene's mass in the Thomas-Fermi regime shrinks rapidly as a function of scale factor. And this is what is sort of shown here. You see sort of a mass as a function of scale factor, and the black curve is sort of the mass that fills the horizon at a given scale factor, and the colored curves are the gene's mass as a function of scale factor, and it drops as a, with A, depending on the choice of Thomas-Fermi radius. So all the way from 1 kiloparsec, which I've shown you sort of the benchmark, down to very small values of 1 parsec, say, as a comparison. And I have mentioned it before, and actually it's very important, but I have no time to go into the cosmology of things. Scalar field dark matter with self-interaction has a non-standard expansion history. So it behaves relativistically in the early universe, and depending on parameters, it might be relativistic up to the time of matter radiation equality. So there is already bounds that you have to observe in order to make sure that the cosmology, the expansion history is not too different from CDM, lambda CDM. But scalar field dark matter with self-interaction, repulsive self-interaction, behaves like realistically, so it has an equation of state like radiation. So W is 1/3 in the early universe. So we had to make sure, okay, we have to say, we have to consider the case when we are in the radiation dominated epoch of the universe, where the scalar field is relativistic, and have to study the growth of modes in this epoch, as well as the matter-dominated epoch. And you have to sort of consider the time when modes enter the horizon, and when do they do this, in which epoch of the universe, and is their mass above the gene's mass or below the gene's mass? If they're above the gene's mass, they can grow, they can go on gravitational collapse and so on. If they're below, they just oscillate. In that sense, very similar to what we have in the standard picture. The point is just the gene's mass in the Thomas-Fermi regime shrinks much more rapidly than in the fuzzy dark matter case, for example. And this has implications. Yeah, this prompted Paul Shapiro to speak about the incredible shrinking gene's mass in memory of a movie of the 50s in the US, sort of the incredibly shrinking man. Yeah, so the point is that the cutoff in the transfer function, the cutoff in the power spectrum that I show you, at much sort of higher K already. Maybe I go already here because it's more intriguing here. Here's a meta power spectrum, black curve is CDM, you will notice. And then you have different scalar field dark matter models. Here, the colored ones are the Thomas-Fermi models, and they have different Thomas-Fermi radius. So you can see they all have a cutoff, obviously. And fuzzy dark matter models in gray, also 2 models, and they also have a cutoff. And 2 things you can see, if a Thomas-Fermi radius of 1 kiloparsec would give you a cutoff that is so high that you would actually cut off the power already at a scale where you would later not form a halo which has a Thomas-Fermi core radius of 1 kiloparsec. So you would wipe that structure out maybe already. So that means that model is in danger to be valid. Of course, if you decrease that scale, the cutoff happens sort of at higher K, so you're better. I mean, you sort of don't cut off too much power. And there's also a difference between the models, right? So it turns out a fuzzy dark matter model with 0.8 times 10 to the minus 22 eV has the same cutoff than a Thomas-Fermi model with a radius of 10 parsec. I mean, the fuzzy dark matter case was a case where you had a big core of 1 kiloparsec, say. And this is the same cutoff in the power spectrum than a Thomas-Fermi model with 10 parsec. So apparently, if that means it appears that only those Thomas-Fermi models survive with small Thomas-Fermi radius. Same here for the halo mass function. Redshift type halo mass function can calculate. It branches off from CDM because there's a cutoff. This is really the same as in the power spectrum. You can see that the Thomas-Fermi colored lines, the cutoff is very early, but then the sort of it's smooth, sort of a shallow slope, while the fuzzy dark matter cuts off later, so to speak, at smaller masses, but then it's sharp, a sharp drop off. And yeah, even in the power spectrum, you can see this, right? It seems much more cut off, sort of like a cliff compared to the Thomas-Fermi models, which are the slope is more mild, fall off is milder. So anyway, yeah, and the same happens even as a function of redshift. So these are all at the same redshift 0. If you look at the redshift evolution, you can see the difference, right? For a fuzzy dark matter case, you can see that the cutoff in the halo mass function away from CDM, which is black, is sort of sharp, and it's nearly not recovering. I mean, if the redshift, if you get to closer redshifts here closer to C equals 0, it does recover, but not a lot. While for the Thomas-Fermi case, you see the curves are really different. Early cutoff, high redshift, let's say, but then it recovers. At lower redshift, the curves do not fall off as steeply, they are milder. So in a sense, the modes are filtered early in this model. They're filtered early, where the cutoff is earlier, but then they recover later again. And so this gives you nuances, new nuances in a sense, meaning if you say you have a minimum halo mass, say, of 10 to 8 solar masses, then in a Thomas-Fermi model with a RTF of 10 parsec, that model has an order of magnitude more halos of this mass 10 to 8 than a fuzzy dark matter model with a mass of 8 times 10 minus 23, we say, but still only 14% of the CDM number. And the same thing you can do for other models. The point is you cut off structure more than you wish, so you have to pick actually a smaller Thomas-Fermi radius than you might want, because you want to have 1 kiloparsec, but it turns out you have to be smaller than 1 kiloparsec. That means you will have more substructure than fuzzy dark matter. You will have more substructure, but not nearly as much as CDM. So now there are wiggle rooms maybe, and maybe there's some interesting thing to gain. Or so it seems not so, yeah, it seems there are nuances which one have to study in more detail. And yeah, just briefly, lately we basically confirmed this previous work, because that previous work was limited in a sense that it was only a semi-analytic kind of linear structure information calculation, while now we used class to do this. And so we actually confirmed the previous things. I showed you power spectrum already. This is the same more or less, except that we plot it down to very small power, because we see that for the fuzzy dark matter cases and the ultralight axion cases, which are real fields, they fall off very quickly and then also recover, but at very low power. It doesn't probably have anything we can do about observations. It's too small. But anyway, just to say that there is some confirmation of this work already with other means. Same for halo mass function. And yeah, again, this is the thing with the baryons included, the poor man's adiabatic contraction thing. Now I come back to the curves I haven't explained. This is the same slide I already showed you before. It's just now I draw your attention to these uppermost curves. And the uppermost is a CDM curve, actually, with a baryon fraction of 0.1. And the lower curve, the greenish one here, is a Thomas-Fermi scalar field model with a core radius of 0.1 kiloparsec. So you can see it is barely distinguishable from CDM once we include baryons. So the point is, if these structure formation calculations, which I just showed you, with the power spectrum and all that, tell you that the Thomas-Fermi radius has to be sub-kiloparsec, I mean much sub, meaning maybe smaller than 100 parsec, then that tells you that we can only pick small cores, but then even in this poor man's calculation, once you include baryons, it seems to have the same issue than CDM. Or in other words, if you have a compact core, not only, I mean a small core, it appears that you have the same issue with CDM again. And why would you have a small core? Because this linear structure formation calculation disfavor the kiloparsec cores. So I'm sorry, I guess I made it somewhat. So the main conclusion is scalar field dark matter provides new twists on small scale problems. I don't want to say it resolves them or does not resolve, but the implications are yet unclear. It appears that fuzzy dark matter is unable to resolve the small scale problems in the sense that once you resolve one, you don't resolve the others. If you are in the Thomas-Fermi regime, there is quite a hard, there's a cutoff which you have to reduce by making the Thomas-Fermi radius small. However, it also appears that the cutoff, the early cutoff, is then milder. So there's still wiggle room in a sense that you might say, okay, what I could have more substructure than fuzzy dark matter, but still much less than CDM. Does that help in the small scale problems? I don't know. If somebody comes and say, oh, maybe we can explain subhalos this way because we find stellar stream perturbations and we need tiny subhalos, maybe we are good, right? But if we want to explain, for example, the cusp-core problem, where it appears that the addition of baryons enhances the deviation to galaxy data, at least in the kind of work we did, then we have a similar problem in CDM. And it seems that the cusp-core problem cannot be resolved due to the dark matter of SFDM, but that it requires baryon feedback after all. So it is somewhat, how shall I say, I was disappointed first to see all this, but it remains to be seen where the model goes and what else one can come up with. And maybe we will not be able to explain the small scale problems, but we still haven't detected dark matter yet, so we may still work on scalar field dark matter for no better other reasons. Okay, thank you for your attention. I'm sorry if I ran late. I was a bit slower than I intended.
No worries. Thank you very much for your talk. It was a nice presentation. And let us now go for questions. I don't know if anyone want to speak or raise their hands. Any questions?
I have a question, but I don't find the hand.
Don't worry, don't worry. Just
Here. Yeah, I saw the hand. Here.
Okay, go ahead.
Okay. More than a question, I have a remark or a comment. What happened if you include, for the people working in cold dark matter, they solve the problem of cusp using supernova explosions, different curves for the stars around the center of the galaxy or something like that. And what happened if we use something, and the criticism from them to the scalar field dark matter is that they observe that, not so much as they need, but they observe some explosions of supernovae and something like that. What do you mean if we include this some supernova explosions or all of these phenomena that they claim to be happened in the galaxies?
Yeah, certainly. It could probably resolve the issue, because what I've shown you here with this adiabatic contraction models, they do not include stellar feedbacks. No? So you could argue, if I have suppose I have to pick a small Thomas-Fermi radius of sub-kpc. If the density is relatively higher there, and if adiabatic contraction increases the density, of course, that means above some threshold, you will have star formation, right? You will form stars, stars will die, there will be supernovae. And so then you have this kind of inverse adiabatic contraction where gas blows out. So the same will happen here, of course. So these curves here are really upper bound limits of the density you might expect. So if I would include baryon feedback in this small core model, I'm sure I could reduce the density again to a level which is fine with the data. Again, I don't know how much feedback you may need for that. Maybe somewhat similar than CDM, if I just look at this. No? Maybe. For sure, I agree that if something works for CDM, say, the same will work for a small core scalar fluid dark matter, I would say. And in that sense, if baryon feedback is the resolution of the cusp-core problem, at least, then the same applies for scalar fluid dark matter as well. Yeah.
Okay. Well, maybe no. Okay. Thank you.
Any other question? Anybody else? I have a somehow silly question. Well, I'm not an expert in the field, but we've been interested in the formation of these kind of structures for other regimes of the scalar field domination. But something crucial for us is the time of formation of the core and of the halo itself. So do you have a grasp on whether this is like far different with fuzzy dark matter or CDM in the case of the Thomas-Fermi regime?
That's a good question. I have no answer at hand, but I should look it up whether one can say something, because I guess what you mean, what are the time scales in forming sort of the core? Here are, as an example, here are time snapshots, these gray lines, and you can see down there, you don't see a core yet, maybe, but one has to be careful because this is sort of, this is a kind of an accretion shock which moves outwards. So it's a good question. When does the core form, right? This is probably and how does it differ in the fuzzy dark matter case? That's a good question. I don't know.
But I guess people are exploring those kind of issues.
I mean, right. And also, it depends also what the initial conditions are, because people, for example, in this fuzzy dark matter simulation, they already start with cores, in a sense, solitonic blobs, whatever, right? And let them collide, no? And then they merge, and there's wave interference going on, and then there's a relaxation process. About which Francesco Guzman would know a lot. Maybe he would be the one to ask this question, actually. And how long does it take, right, sort of to build up this central core, which then is surrounded by this more wavy kind of envelope? Yeah, I don't know, but it's a good question.
I think Tonatiuh has another comment. Is that right?
Yes, I have another question. All your two results depend very strong from the mass of the scalar field. For example, you write 10 to the minus 22 electron volt, 0.5 and 2.5 and something else, no? And what happens if you change this mass? For example, it is possible that the scalar field has another not this mass but an effective mass, for example, given by the some transformation or something like that. With this mass, you will have another results. Is it possible to change the mass and then to solve this problem of the consistency between the too big to fail and the center of the galaxy and so on?
Yeah, so I guess I could say two things. I mean, in fuzzy dark matter, where you only have the mass, there is this scaling transformation, right? So you can sort of change the parameter, the mass, say, and then you know what factors come out in your overall scaling. So, for example, Watch et al., they claim that sort of you can rescale their results. In the Thomas-Fermi case, it's not the same, but I would think, well, for example, for this issue, I think maybe your question goes into the direction of what if can I find a mass which still can solve both of these problems, maybe, right?
Yeah,
maybe
that's right. That's my question. Exactly. That's my question. Mm-hmm.
Yeah, that's a good point. I mean, these people consider two cases, one of which was just motivated by some simulation by Shive et al., and the other case is also a benchmark. Yeah, I don't know. Maybe there is still a case where you can do better. Mm-hmm. But it's also true that the bounds on the mass for fuzzy dark matter get higher and higher, right? So that the lower bound estimates get higher and higher. So people lately have used local group dwarf galaxies and claim that means that the Breuil must be smaller than 500 parsec or something, which is equivalent to something like what is it? 10 to the minus 21 EV even, or something. So even a higher mass than this one, almost a factor 10 higher already. The same for Lyman alpha bounds, right? People have said, oh, using Lyman alpha bounds, you get 10 to the minus 21. I'm not trusting so much to Lyman alpha bounds because there's a lot of other. But the problem is when for fuzzy dark matter, if the mass becomes too high, in a sense, this is related to if the Thomas-Fermi radius becomes too small. So you're back to the problem that your core is relatively small. And then you may not resolve the small scale problems. Or in the fuzzy dark matter case, here it's worse because rho, the central density goes like mass m to the 4. So if your mass gets higher, your de Broglie gets smaller. That means you have more and more mass into that smaller region, and you get much higher densities in the center. So maybe there's still some wiggle room. And in this paper, they just picked two models, right? I mean, they just wanted to make a case, I guess. It's not to certainly prove. These are now rigorous papers, all of these. I mean, also ours. I mean, we don't fit. In a sense, we do not fit here even, right? We just say, okay, which models would represent the data well? So these are plausibility things more than really proofs of a kind. But it points to a direction. It points to saying, okay, for fuzzy dark matter, if the mass seems to getting up because of constraints, that means the core is getting small. And in the Thomas-Fermi regime, where I'd hope that we can have 1 kiloparsec cores, unfortunately, the linear structure story down here seems to say, no, the cutoff is too high. You would wipe out too many halos in the first place. And so you actually need smaller Thomas-Fermi radii in the model, which is equivalent to saying that fuzzy dark matter mass is much higher than originally.
Yeah, I see. Okay. Thank you.
Great. Any other questions or comments? If not, well, then let's thank Tanja again. Thanks a lot for your participation. Thank you for being with us.
Thanks for the invitation. It was a pleasure.